Hello everyone, welcome to the final project presentation for the finite element methods. We are two group members, Monisha Soliprum and myself, Mamoon Shafi. The topic of our project is finite element analysis of steel in uniaxial tensile test. Problem background. The tensile test is one of the fundamental tests to determine mechanical properties of steel. During the test, bottom of the specimen is usually fixed and the top is imposed displacement. To maximize the chances of rupture happening in the middle section instead of the gripping area, we're using the dog bone shape, which is the most common shape for testing the samples. Speaking of the finite element model, we used 3-node triangular elements in a dog bone shaped sample which was 100 millimeter long. The boundary conditions set up were that the bottom was fixed and the top is imposed displacement. The material used is AISI type 3161 stainless steel with an ultimate tensile strength of 560 megapascals. The Young's modulus is 193 gigapascals. The Poisson ratio 0.3. Coming over to the formulation for the finite element method. These are the derivations. First we have the weak form, and then we have the constitutive equation, followed by the shape function for the 3-node triangular element. Here is the relationship between the displacement and strain. So here is the Jacobian, and by comparing and solving for all the above equations and relationships, we get down to the elemental stiffness matrix, and combining all the elemental stiffness matrices, we get the global matrix. Then we can impose the boundary conditions and therefore we solve the problem. Domain discretization. To be able to do our calculations in our master domain, here we use a 4-point case for the Gauss points, that is shown in the graphical illustration as cubic. Now a word about code implementation into MATLAB. We set the step of displacement on boundary condition as 0.02 millimeters, calculating the stress for each step. We stop the loop when stress on the tensile direction reaches the ultimate tensile strength of 560 megapascals. That is to check the strain for the rupture. So here we have the results in the form of 3 graphical representations: displacement field, strain field, and the stress field. Take a look at the displacement field. We can see that the maximum displacement at the time of the rupture is around 0.2%. Moving on to the strain field, at the time of rupture, the maximum strain is around 0.25%. Now the stress field, which is almost behaving similar to the strain field, we can see the maximum value goes to around 560 megapascals when the rupture happens, and that is what we set up right in the beginning, and this is what we expect. The rupture displacement is 0.18 millimeters. The local rupture strain in the middle section is 0.26%. Considering the fact that in uniaxial tensile test, rupture strain is usually calculated by delta L over L from experimental data, the rupture strain here can be considered 0.18%. Thank you very much. That would be all for the abstract for the project presentation.